This video will cover the topic, graphing a piecewise defined function, problem type 3. As we have previously learned, a piecewise defined function is a function split into multiple pieces with different domains. Problem type 3 will deal with a mixture of quadratic and linear functions. Let's take a look at our example. Suppose that the function f is defined for all real numbers as follows. F of x equals x squared plus 1 if x is less than 1, 2 if x equals 1, and 7 minus 5x if x is greater than 1. Graph the function f, then determine whether or not the function is continuous. We can see here that f is split into three pieces with three domains. The first piece is x squared plus 1, which is a parabola, so we will start by graphing x squared plus 1.
When I graph this, do I graph only the piece, or do I graph the whole parabola first and then cut it?
Great question! We will first plot the point at the end of the domain, then we will graph the whole parabola, and then we will make the cut. We will start by plotting the endpoint, which we can see will be at x equals 1. By substituting 1 in for x and x squared plus 1, the y value will be 2. At 1, 2, we will plot an open circle because x is less than but not equal to 1. Now to graph the parabola, we start at the vertex, which we find to be at 0, 1. If the concepts of graphing parabolas seem unfamiliar, it would be good to review the video graphing a parabola of the form y equals ax squared plus c before continuing. Now because the leading coefficient of the quadratic is positive, the graph will open upwards. In Alex, after choosing the vertex and the opening direction, we would then plot the next closest point, and then the graph will be generated. Because the vertex is at x equals 0, one of the next closest points will be at x equals 1, which we already know is 1, 2. We can plot the next point there, and the corresponding symmetrical point to this one is -1, 2. We draw the graph from here. Now in Alex, we plot the cut point at 1, 2, because we know that this is the endpoint, and if x is less than 1, we have to erase the part of the right of 1, 2, where x is greater than 1. Now the next part of the function is a solid point at 1, 2, so this will fill in the open circle at the endpoint of the parabola. Now why is this? Because looking at the second part, we see that y equals 2 if x equals 1. This means one solid point. Now we have a linear expression, 7 minus 5x, when x is greater than 1. We will plot the first point of the line at x equals 1. By substituting 1 in for x in the expression, the y value is 2. We would normally plot an open circle here, but because 1, 2 is already included, we leave it as a closed circle. We can see from the expression that the slope of this line part is -5. Start at the endpoint, and we move down 5, and right 1, and plot the next point, which is 2, -3. We then draw a line from here, and we now have the full function plotted.
How do we determine whether the graph is continuous?
A graph is continuous if it is a single unbroken curve that can be drawn without lifting the pen. If there are any jumps, holes, or vertical asymptotes within the domain, then the graph is discontinuous. In this function, if we only looked at the first piece, there would be a hole at 1, 2, making it not continuous. But the second piece filled in that hole. After that, the line continues on to infinity, so this graph is continuous.
Okay, so to graph a piecewise defined function that has a mixture of a quadratic and a linear expression, I start by graphing the first part of the function and following the domain. Then I graph the next part, following the next domain, and then I graph the last part, following that part's domain. When I need to cut a part, I plot a cut point at the needed point, and then I can delete a part on either side of the cut point.
Very good. Now you're ready to graph a piecewise function.